Welcome back, everybody. We're in the Chapter 12 lecture note outline, and we're here on page number 9, where the last time we left off talking about units of concentration. So we talked about molarity and percent by mass and percent by volume. And we ended the last lesson learning about the C1V1 equals C2V2 equation for helping us with dilution calculations. Let's try a few more examples of calculations that involve dilutions here at the beginning of page 9. Because we can use the C1V1 equals C2V2 equation to help us with dilution calculations, it's a good idea to write down all of those parameters in the left-hand margin when you're starting out one of these problems. So reading through this problem, we see that the initial concentration is 1.50 molar, the initial volume is 53.4 milliliters, the final concentration is 0.800 molar, and the final volume is what we're looking for, what we're trying to solve for. So if we isolate the V2 variable from the equation C1 times V1 equals C2 times V2, we get V2 is equal to C1 times V1 over C2. We just need to plug in our values for the concentration, volume, and the final concentration, and then we can solve this equation for V2. Notice that because we have units of molarity at the top and at the bottom, these units cancel, and we're left with the units of milliliters. Notice also our parameters have 3 significant figures, so our answer here should also be rounded down to 3 significant figures. So we get 100 milliliters, and that's 3 sig figs. So if you got that right, great job. Now try this next example out. It uses a different unit for concentration, that being percent, but you can still solve this in the same way. So just give it a start by writing down C1, V1, C2, and V2 over here on the left, and then try to solve for the missing parameter. Okay, so now that you've had a chance to try this one out, here's the solution. So far, everything is pretty much the same as the problem up above, the previous problem, except here we have a different unit for concentration. We have the percentage. Now notice that we have the percentage here in the numerator, but we don't have it in the denominator. We have milliliters in the denominator. So milliliters will cancel with milliliters, and we're left with the unit of percentage. So our final answer here is 6.25%. Now if you got that right, great job. Now this last example has a number of extra steps we have to perform before we can actually solve C1V1, C2V2. Mostly what's going on here is we're missing the initial concentration. That first concentration we need to actually find. We're given the mass of the solute and the identity of the solute, but we have no idea what the molarity is. So the first thing we need to do is recall what molarity is. Molarity is moles of solute in liters of solution. So first we need to find the moles of the solute. To do that, of course, we need the mass and the molar mass. So we have the mass here. It's 0.246 grams of copper 2 sulfate pentahydrate. Now for every mole, how many grams is that? And how would we know that? Well, that's right. We have to actually calculate the molar mass here for copper 2 sulfate pentahydrate. So here's how we go about doing that. We have to add together the copper, the sulfur, the 4 oxygens, and the 5 water molecules. The atomic masses, of course, are on the periodic table. So we have 63.5, 32.1, we have 4 times 16 for oxygen, and then water is 18.02 for each one, and since we have 5 of them, it's 5 times 18.02. So we get to 249.7, that's grams per mole. And when we calculate the moles from this 0.246 grams, we get 9.85 times 10 to the negative 4th moles. That's how many moles we have dissolved in the solution, which is 50 milliliters. So now we can calculate the molarity just by dividing the moles by the volume, of course converting that volume into liters. So the way I often do this to save myself drawing all of these steps is I just divide by 50 with those 4 significant figures, but then I divide that 50 by 1,000 inside of the equation. That converts milliliters directly into liters, right? Because it's 1,000 mils per liter. So now that we have this, we can find the molarity, which turns out to be 0.0197 molar. So that's the value for our variable C1. It's 0.0197 molar. Our initial volume, the amount we took out of that solution to dilute, is 2.5 milliliters. We're diluting that 2.5 milliliters to 50 milliliters. Now we just have to solve for the missing variable, which is C2, or the final concentration. C2 will be equal to C1 times V1 over V2. So now I'm just putting in the values for the initial concentration, the initial volume, and the final volume, and then seeing which units are canceled and which units will remain. Notice that we have volume in the numerator and the denominator, and those are both in milliliters. So milliliters will cross-cancel. That means we're left with molarity, and we get 9.85 times 10 to the minus 4 molar. Now, you might notice that molarity happens to be the same as the number of moles that we actually calculated that are dissolved in the initial solution. Will that usually be the case? No. This is a coincidence based on the values that I happen to pick for this particular example, as well as the molar mass for this particular compound. It's a coincidence that won't normally happen, but in this case it does. Okay, so now that we've finished those examples, let's go to the next page and learn about electrolytes. The term electrolyte is used to describe the ability for a particular substance to behave as an electrical conductor when it's dissolved in water. Some substances, when they're dissolved in water, do not conduct electricity at all, whereas others conduct it very strongly. Still yet, some substances only conduct small amounts of electricity when they're dissolved in water. And this is why some substances are classified as non-electrolytes, whereas others are strong electrolytes, and still yet others are weak electrolytes. The simple experiment that I've depicted in these pictures up top with the light bulb is set up like this. We have a light bulb that is connected to a power source, namely the wall. However, the other line to the power source where the electricity needs to make a circuit going through the light bulb to the wall is actually severed. So there's no connection between this wire, the black one, and the white one, except through this solution. Now, if this solution has an electrolyte in it, we have the situation like this, where the electrical current can flow through the light bulb and then back to the wall, and we get a circuit, therefore the light bulb lights up. So a strong electrolyte, we get that current passing through the entire circuit. In a weak electrolyte, it only weakly passes through it, and then in a non-electrolyte, like over here, we don't get a complete circuit at all, and therefore the light bulb does not light up. So let's make some notes about the differences between non-electrolytes, strong electrolytes, and weak electrolytes, keeping this experiment in mind. Non-electrolytes are solutes whose solutions do not conduct electricity. So when we take one of these substances and we dissolve it in water, and we test whether or not we can pass current through it, we get a situation where no current is passed through. That would be like this light bulb example up here. Examples of non-electrolytes include sugars, oils, and gasoline. These are examples of molecular compounds, and it turns out most molecular compounds do not conduct electricity when they're dissolved in water, and so therefore we classify them as non-electrolytes. Strong electrolytes, on the other hand, are solutes that do conduct electricity when they are dissolved in water. In fact, they very strongly conduct electricity when they're dissolved in water. Examples of strong electrolytes include ionic compounds and strong acids. If you take an ionic compound like sodium chloride or a strong acid like hydrogen chloride and you dissolve it in water, you'll get a situation when you set up this experiment up here like this. When we connect the light bulb to the power source, it immediately illuminates very brightly. So therefore, we classify these compounds as strong electrolytes. Now, what about weak electrolytes? Weak electrolytes are solutes that also conduct electricity, however they do so very weakly. When these solutes are dissolved in water and then they're connected to the experiment I was showing you above with the light bulb illuminates but very dimly. That's because the efficiency of that conductivity of electricity is not very strong. Examples of weak electrolytes include the weak acids. A classic example of a weak acid is acetic acid, or HC2H3O2. When acetic acid is dissolved in water, that solution only weakly conducts electricity, so we classify it as a weak electrolyte. Now, why are some substances weak electrolytes and others strong? What causes this difference? Well, it turns out the cause of this has to do with the different way strong electrolytes ionize in water versus weak ones. Specifically, strong electrolytes ionize completely in water. What I mean by that is they 100% turn into ions when they're placed in water. Weak electrolytes, on the other hand, do not ionize completely in water. Here's an example. If we look at hydrochloric acid, or HCl, when we dissolve HCl in water to make a, say, 0.1 molar solution, 100% of that HCl is ionized as H+, or hydronium ions, and chloride anions. So we have 0% of the molecule, which is neutral, and 100% of it ionized as charged particles. Now, it's a strong electrolyte, and that has to do with the fact that we have all of those charged particles in the solution. Those charged particles can move around under the influence of an electrical current, and that's why we get a strong electrolyte. Now, acetic acid, on the other hand, is a weak electrolyte. When it's dissolved in water to give, say, a 0.1 molar solution in water, only about 1% of the molecule is ionized as H+ and acetate anions. So we have 99% of it sitting in that neutral molecular state, and 1% of it, only about 1% of it, in the ionized state. This is why it's a weak electrolyte, simply because there are so few ions in solution after it's dissolved in water. So strong electrolytes ionize 100% in water, whereas weak ones do not. So now that we've talked about electrolytes, let's talk about the next section, which is part 6, colligative properties. A colligative property is a special property of a solution that changes when the concentration of a solute also changes. A few examples of colligative properties include vapor pressure, boiling point, freezing point, and osmotic pressure. So let's go to the next page and start learning about each of these types of colligative properties. So the first colligative property we're going to look at is vapor pressure. Remember that vapor pressure is the pressure that is exerted by a gas that forms above a liquid as it evaporates. That's called vapor pressure. And it turns out vapor pressure is a colligative property because it changes as the concentration of a solute in that liquid also changes. So let's look at how that works with a diagram. So the first thing I'm going to draw in this diagram are two representations of a sealed container. And inside the sealed container, I'm going to also draw a liquid. So let's put that down at the bottom. And in this first beaker, let's call that liquid a pure solvent. Why is it a pure solvent? Well, that's because there are no solutes dissolved in it. So it's just the liquid. Now, as that liquid sits inside of that sealed container, some of them will go into the gas phase because they have enough kinetic energy to escape the liquid phase. These gas phase particles from that pure solvent are in the vapor phase, and they exert a pressure on the walls of the container. This pressure is what we call the vapor pressure. Let's think about what would happen if we dissolved a solute in the solvent to give a solution. How would the presence of this solute affect the vapor pressure of the liquid? The presence of the solute in the solvent to give this solution introduces additional intermolecular forces. These additional intermolecular forces are attractive. What that means is the solvent particles are attracted to the solute particles. This causes a decrease in the vapor pressure because there are less molecules escaping to the gas phase. We can summarize this by saying that increasing the concentration of the solute causes a decrease in the vapor pressure because of those increased attractive forces between the solvent and the solute. So vapor pressure is a colligative property because it depends on the concentration of a solute. When the concentration of the solute goes up, the vapor pressure goes down. They're inversely proportional to one another. So, does salt water evaporate faster or slower at a constant temperature compared to regular water? That's right, it evaporates slower. That's because salt water has a lower vapor pressure as the result of an increase in the concentration of the solute, that being salt. So it turns out boiling point, the temperature at which a liquid boils, is also a colligative property. To understand how this colligative property works, let's look at a diagram. Similar to the diagram I drew above, I have two sealed containers, each containing a liquid phase. The container on the left contains a pure liquid, whereas the container on the right contains a solution. Now what we're talking about is the difference in the boiling point between this pure liquid and the solution. Recall that the boiling point is the temperature at which the vapor pressure is equal to the atmospheric pressure. So I've tried to represent the vapor pressure and the atmospheric pressure here in the pure liquid with arrows pointing up and down respectively. Now notice that these arrows are the same height. That's because supposedly I'm at the boiling point for this liquid. That is, the temperature at which that vapor pressure is the same as the atmospheric pressure. Now what do we know about the change in the vapor pressure when there's a solute in a solution? Well, that's right, when we have a solute dissolved in a solution, we decrease the vapor pressure. Here's what that looks like. Notice in the container with our solution, we have a lower vapor pressure than in the container with the pure liquid. We just learned that vapor pressures decrease as you increase the concentration of a solute, so this is the expected result. Now, if these two containers are at the same temperature and the one on the left is boiling, what about the one on the right? Well, that's correct. It is not boiling. It is below the boiling point. That's because the vapor pressure does not equal the atmospheric pressure. Now, we could eventually boil this solution if we continue to raise the temperature, because raising the temperature would increase the vapor pressure, and eventually that vapor pressure would equal the atmospheric pressure. But note that this solution with the solute in it has a higher boiling point than the pure liquid. That's because we've decreased the vapor pressure. So to summarize the effect of the concentration of a solute on the boiling point for a solution, we can say that as the concentration of the solute increases, the boiling point also increases. This is why we call boiling point a colligative property. It's because it's a property that changes as the concentration of a solute also changes. So we've learned so far about two types of colligative properties: vapor pressure and boiling point. Let's go to the next page where we'll learn about melting point and osmotic pressure. So a substance melts when it converts from a solid into a liquid. It freezes when it turns from a liquid into a solid. The temperature at which it does this conversion is called the melting or freezing point for a solid. And it turns out that melting/freezing points are also a colligative property. As we increase the concentration of a solute that contaminates a solid, we decrease the melting or the freezing point. This is often referred to as the freezing point depression, because as we increase the concentration of some contaminant in a liquid, we lower its freezing point. We actually use this all the time here in Idaho when we're trying to prevent water from freezing on our sidewalks and our driveways. We do that by adding salt to all of the water. Increasing the concentration of the solute, salt, in water lowers the point at which it freezes. So the melting or the freezing point is also a colligative property. We have one more colligative property to talk about, and that's osmotic pressure. So in words, osmosis is the tendency for a solvent to move across a membrane in order to establish a balance or an equilibrium across that membrane. It does this by moving from a less concentrated area or side of the membrane to a more concentrated one, thus diluting it. So I think it's easier to understand this if we look at a diagram. So let's draw one. So imagine we could zoom in on a very small tube, something like a capillary tube. And across this tube, we had what's called a semi-permeable membrane. Now, this thing that I'm calling a membrane is a type of material that allows certain types of molecules with certain properties to pass through it where others cannot. And lots of different examples of semi-permeable membranes can be found. So for example, a plastic bag is actually a semi-permeable membrane. The type of material it's made out of is a lot like the semi-permeable membrane that I'm showing you here. The semi-permeable membrane that I want to show you is one that allows water to pass through, but not ions. So in a situation like this, we have a difference in concentration on the left and on the right. The blue dots here on the left and the right represent water molecules, whereas the red dots represent solute particles. Notice the concentration of the solute is much higher on the left than it is on the right. Now, because water can pass through the membrane and the ions can't, what happens is the water migrates from the right to the left in order to establish a balance of concentrations. This has the effect of increasing pressure across that membrane, and this is called the osmotic pressure. Now, water desalination plants use osmosis in reverse in order to purify water. What these plants do is apply a pressure equal or greater to the osmotic pressure in the reverse direction. This is called reverse osmosis. By applying the osmotic pressure in the reverse direction, it's possible to purify water from the high concentration of ions that are on the left by forcing the water across the membrane, leaving those ions behind. This reverse osmosis process definitely requires energy, so it is not without its costs. But osmosis isn't just limited to purifying water, it also has a lot of biological implications. Let's go to the next page where we'll learn about the effect of osmosis on cells. So it turns out that cells are encapsulated inside of a semi-permeable membrane. We call this the cellular membrane. Now, because cells are in an aqueous environment and they also contain a solution inside of them that is mostly water, they are definitely susceptible to osmotic pressure. When biologists are studying cells, like your red blood cells, for example, they talk about the different types of solutions that the cells are prepared in. They describe these solutions as being hypertonic, isotonic, or hypotonic, depending on the concentration of the solute in that solution. So, for example, a hypertonic solution is a solution that when a red blood cell is placed in it, the water leaves the cell, causing it to shrivel up. Compare this with a hypotonic solution. A hypotonic solution is the exact opposite. We end up seeing water flow into the cell. This can cause it to burst. Now, an isotonic solution is one in which the cell doesn't either gain water or lose water, but it stays the same. So try to figure out in each case where the higher concentration of solute would be. Would it be inside the cell or outside the cell? So to help you with this, remember that water will always flow from the less concentrated side to the more concentrated side in order to dilute it. So in a hypertonic solution, we're seeing a higher concentration outside the cell. That's because water is leaving the inside of the cell to dilute the outside of the cell. In a hypotonic solution, on the other hand, water is flowing inside the cell. This is to dilute the higher concentration inside, so the water goes in to do that. In an isotonic solution, we have an equilibrium between water flowing in and water flowing out. That's because we have a balance of concentration both inside and outside of the cell. So to recap what we just talked about, we learned about 4 different types of colligative properties. Colligative properties are properties that vary with concentration in a solute. So we learned about boiling point, vapor pressure, melting point, and osmotic pressure. So for each of these types of colligative properties, make sure you, of course, you know what it means, but also know how it changes in relation to a change in the concentration of a solute. With that, let's go to the next part of this lesson, which is titration. As you're learning in lab, titration is a method or a technique whereby we determine the concentration of an unknown by using a known. Fundamentally, titrations involve 3 components. First, we have a solution with an unknown concentration. I'll call this our unknown. Second, we have a solution that has a known concentration. I'll call this our known. Third, we need an indicator. The indicator is a special molecule. It's a molecule that changes color at something called the endpoint of the titration. I'll explain what an endpoint is here in a minute and why the indicator changes color at the endpoint. But first, let's look at a diagram of a typical titration. In a titration, we take our known solution and we put it into something that we can measure it with. Usually this is something called a burette. And I've labeled the known here A. So we take this thing called a burette, which is basically a long column that has markings on it indicating the volume. It also has a knob at the bottom that allows an amount of that A to flow through it. Now, right below our burette, we have an Erlenmeyer flask, which contains our unknown. I have labeled our unknown B, and we've also added a small amount of the indicator to this B. Now, how the titration works is we gradually add our known to the unknown, and at some point we reach an endpoint, and at the endpoint, the indicator changes color. Let me walk you through how that actually works. First, A, our known, is gradually added to B in that Erlenmeyer flask. Now, A and B react together, and because they react together, that small amount of A that I added is no longer there, neither is a small amount of B. They've reacted together and go away as something else, say C. Now, eventually, enough of A is added to consume all of the B that was present. Now remember, we didn't know how much B was there, but we just keep adding a small amount of A until all of the B is gone, and then we stop. This is called the endpoint. So how do we know when we actually reach the endpoint, the point at which all of the B has been consumed? Well, that's right, that's because of the indicator. After all of the B is consumed, any additional A that is added after this point starts reacting with the indicator. When it reacts with the indicator changes color. This is how we know we've reached the endpoint. Now, if we know how much of A we added and we know how many B molecules reacted with it, it turns out that means we can establish the concentration of our unknown. On the next page, we're going to see how we actually do this with a real example. Let's go take a look. In this example, we see a titration problem. It tells us if 28.3 milliliters of a given concentration of sodium hydroxide, that's our known, is needed to reach the endpoint of a titration with 25 milliliters of the unknown, what is the concentration of that sulfuric acid? So let's see how we set this up. It's a classic titration example. So with any titration problem, we want to first make sure we're dealing with a balanced chemical reaction. So I've written out the reaction here, which is sulfuric acid reacting with sodium hydroxide, turning into sodium sulfate and water. Now, this is all the correct formulas with the right subscripts, but I need to make sure I go ahead and balance it. See if you can do that first. So if you figured out that we need a 2 coefficient in front of sodium hydroxide and a 2 coefficient in front of water, great job. Now let's figure out how to solve this problem. The first thing we need to do when approaching this type of problem is we need to figure out how much of the known we actually used. Now we see that 28.3 milliliters was actually used, and we're also told the concentration of that known. So it turns out from this information, we can figure out how many moles of sodium hydroxide were actually added to reach the endpoint. We need to convert the volume, or milliliters, into moles, and we do this by using the molarity as a conversion factor. Now we know how many moles of sodium hydroxide, our known, were actually used to do the titration. What do we do next? Well, what we're interested in is the concentration of the unknown. To determine the concentration of the unknown, I need to know how many moles there were. So I'm going to figure out how to convert moles of our known into moles of the unknown. This would be a good point to pause the video and see if you can do this conversion on your own. We start with the 0.0312 moles of sodium hydroxide that we calculated in the previous step, and then we multiply it by a conversion factor that goes from moles of sodium hydroxide into moles of sulfuric acid. That's our unknown. Now, where do we get the values for this conversion factor? Well, that's correct. We get them from the reaction equation. So we can convert our moles of sodium hydroxide into moles of sulfuric acid simply by multiplying by this mole ratio, which is 1 to 2. Now, how do we figure out the concentration of the unknown? We have the moles. What do we need to determine its molarity? Well, that's right. We need the volume. If you take a look at the problem, it says that we used 25 milliliters of sulfuric acid. So the molarity is just this 0.0156 moles of sulfuric acid divided by 25 milliliters converted first into liters. I've shown that here as just 25 divided by 1,000, since that's how we go from milliliters to liters. When we do that, we get 0.0624 molar. That's the molarity of the solution that we titrated. So this is how a typical titration goes. We start with a known. We know the concentration, and we titrate an unknown until we reach the endpoint. At the endpoint, we measure the volume of the known that was used. From the molarity, we're able to calculate the moles of the known that were used, and therefore the moles of the unknown by the chemical reaction that is involved between those two. Once we know the moles of the unknown that were actually titrated, we easily turn that into a concentration like molarity just by dividing moles by liters, for example. So with that, I'm going to end this lesson. Please let me know if you have any questions, and I will see you soon.